Morning, guys. So yesterday we had a look at the Rydberg equation. We found that for single electron species like hydrogen, the Rydberg equation actually gave us a relationship between the shells that the electrons themselves are jumping, especially when electrons fall from a high shell to a low shell, emitting off a photon with a certain color. So I'm just going to give you a quick warm-up question based on that, and then today we're going to be into our newer model here called Electron Configuration. We're going to find places where the Bohr model actually is insufficient, and we actually need to modify that a little bit. So let's just start off here with a warm-up here. This question is worded, which electron transition, so from which shell to which shell, which electron transition releases a photon? So this is light energy that's going to be leaving the system. Releases a photon with a wavelength 656 nanometers. That actually corresponds to the red wavelength that laser pointers are actually using in the Balmer series. So let's just try this question here just for practice here. You might need to refer to your notes from yesterday for some of the constants and the equations. As always, I like just sort of deciphering through the problem here. They give us wavelength here at 656 nanometers, so that one there is going to be a lambda. Remember, we want to re-express that in terms of meters, so it could be 656 times 10 to the negative 9. Your calculator will very quickly shorthand that to 6.56 times 10 to the negative 7. That's perfectly okay because I had 600 or so nanometers. That gives me 6 in the 10 to the negative 7 place. In this case here, they do use the terminology Balmer. Balmer tells me two things. Balmer tells me that we are looking at the hydrogen atom, so that means my Z atomic number is 1. And Balmer was actually looking at a series. If I focus in on n equals 2, and I focus on all the transitions falling to n equals 2, those belong to the Balmer series. So just by telling you that word Balmer, I'm expecting jumping from some higher shell than 2, the electron is stuck on the atom, the electron falls to 2, and then when it releases energy, it needs to give off energy exactly corresponding to 656. So the question here is using the Rydberg equation. So let's try 1 over lambda is equal to rz squared, 1 over ni squared minus 1 over nf squared. So that was the Rydberg equation from yesterday. Let's try it out here. I'm going to purposely leave in a mistake for now. So 1 over the wavelength. The wavelength I want is 6.56 times 10 to the negative 7. You can still copy it down. I'll tell you when to stop copying. The Rydberg equation is 1.097 times 10 to the 7. We are looking at hydrogen, so this is element number 1. We need to take element 1 squared, and then we need to go 1 from the starting shell. That's the question. I don't know what starting shell we are, but based on an energy level diagram, we're looking at there's shell 1, there's shell 2. We're probably some higher shell here, and then we're falling down to shell number 2. So my n initial is the question. How high am I starting off from? But I do actually know that the n final is equal to 2. So I'm going to leave this as a constant here, ni squared minus nf. That would have to be 2 squared there. So let's just plug our way through. Since the Rydberg gives us the relationship here, let's see what it tells us. I'm just going to copy the whole number down. Calculator spits out 1524390 and a couple other decimals here. I still have Rydberg's constant out here. I'm going to bring that to the left-hand side. I'm going to have a 1 over ni squared. 1 over 2 squared is 1 over 4. So let's just divide the Rydberg constant over. So take the 1524, that number there, divide it by Rydberg. This gives me here 0.139 equals our 1 over ni squared minus 1 over 4. As usual, I don't want to deal with fractions, so what I would do here is I would just convert that to decimal. At this point here, you can stop copying because remember I purposely left a mistake. Let's see if we can find what it is. So let's just work through the math here. Let's just add 0.25 over. That gives us easy 0.389 is equal to 1 over ni squared. To get the ni, I need to take the reciprocal, the upside down of this. 1 over the 0.388 gives me 2.57 is equal to ni squared. Now I'm super close to ni squared. Ni, once I take the square root here, is actually telling me ni is 1.6. Couple problems with that, right? So first thing is, if you remember what ni is a measure of your starting shell. Where does your electron begin? Remember, your electron shells are quantized. They come in like a staircase. They come in set floors. They can't come in 1.6. An electron can't be on 1.6. There is no place to sit. That isn't one of the steps that it's allowed to actually be on. Let alone, even if that were the case, even if 1.6 could exist, if 1.6 jumps to actually 2, it's actually having to gain energy. This is not going to release a photon at all. So what's the problem here? Why isn't my math actually giving you the correct answer? The problem that I sort of left here is you'll notice that this thing here is actually releasing off a photon. Energy is actually leaving the system. We saw in the Rydberg equation it was great for absorption as positive. If this is an emission process here, we actually need to put a negative. It doesn't mean somehow the wavelength is negative. Wavelength is a distance, has to be positive. But remember, negative means this photon here actually ends up leaving the system. It takes this energy away with it. So what I left here is I actually need to put in the negative. If you look at the questions from yesterday, the negative sort of came out in the calculations. This time, because I didn't have it yet, because I saw that term release, I'm going to put a negative there. So now you can go through with the negative there. At this point here, when I told you to stop copying, and I add the 0.25 over, now with the correct sign there, this one ends up being 0.111, so you can copy this one here. Take the reciprocal of that there, that gives us pretty much 9. And therefore, if you take the square root of 9 here, it's actually going to be 3. So we sort of fix our problem here. So the initial level not only is a whole number, it's also a number that's bigger than 2. So when the electron actually falls from 3 to 2, this gap size is actually big enough so that when the photon ends up leaving, that photon ends up taking with it 656 nanometers of energy. All right, so make sure you do some practice with the Rydberg equation and just be comfortable using some of those constants there. Today we're going to just flesh out this idea a little bit more here. Yes, energy levels here are quantized, but one of the first things that we're going to see in the new model is that each of these levels can actually be subdivided into multiple levels. So this is getting us into another model here called Electron Configuration. You're going to find this energy level diagram under the resources column here. We'll come back to this in just a second. And then on the back side here, there's a nice memory aid for the types of questions that we're going to do. Again, we'll come back to it as we have explored this model a little bit. So just starting off our notes for today here, you can just call this one here Electron Configuration. This is a model that basically modifies the Bohr model. Remember, the atom has always been the atom. It isn't evolving. It's just as we get more data, as we get more experimental evidence here, our interpretation of the atom, when we say we discover the atom, our thinking of the atom actually changes. So we're going to start off here with electron configuration here. The Bohr model. The Bohr model actually has limitations, right? There's no perfect theory. We still learn it though, because it gives us really good predictions. We'll come back to in chapter 4. It's perfectly good in predicting bonding and all that, so it's important to learn it. But at least pertaining to this chapter 2 and chapter 3 as we head into it here, the limitation is the fact for the Bohr model, unfortunately, we have sort of, here's our nucleus. Unfortunately, the Bohr model sort of says here, well, electrons are going to be shell number 1, shell number 2. It really doesn't differentiate. Well, each of these shells may actually be subdivided into multiple shells. So the Bohr model actually has limitations since electrons are not actually in orbit around the nucleus. Right. This is when you go back to your junior science teachers, they'd be like, what? Why'd you teach me this? Right? But again, it's not that it's wrong, but it's just that it's incomplete. So one of the first fixes that we're going to take here is, yes, based on Bohr's experiments with line spectra and all that, he had discovered for whatever reason electrons had to be on many different energy floors. Energy levels are quantized. It is more like a staircase, each with discrete energies. There's no energies in between. However, when I take these energy levels, or what are called shells, I count them inside outside, each of these shells can actually be subdivided into subshells. So energy levels are quantized, though these shells, another name for energy level, shells can actually be subdivided into subshells, or using the terminology of, let's say this is an orbit around the nucleus. We're going to call these ones here orbitals. Just for starters, just introducing to you just sort of the lettering and recognizing which subshell it is. This is going to come to us as very strange letters if you haven't seen this before. We're going to call these subshells here either S subshells, P subshells, D subshells, or S subshells. And really, they're just placeholders. We'll come back 2 lessons from now to actually draw what these shapes actually look like. But basically, this is just trying to subdivide some of these floors for us here. So The advantage here is in the Bohr model, we had the different shells here. We had started switching over to energy level diagram. So shell number 1 was, let's say, down here, shell number 2, shell number 3. What I'm saying here is, although the Bohr model makes it seem like, well, electrons that are entering the first orbit, let's say 2 electrons on the first orbit, they seem identical. In fact, we need to be a little bit more careful. Which one of these shells, S, P, D, or F, is it on when it's on floor number 1? Now, I did that in a particular order for a reason, because it's actually going from low energy to high energy. Turns out we actually need to get upwards into the really high shells before we actually start seeing the P's, the D's, and the F's. So first floor here is still relatively boring here. So far, we just said n equals 1, shell number 1. Floor number 1, every single element will have a 1s subshell. It's basically on floor number 1, and it's going to be an S kind of room. Electrons later on is going to have a property called spin. So we're going to put either spin up or spin down. So instead of drawing the single dots, as you may imagine from the Bohr model, drawing them absorbing and emitting like we did the last lessons here, we're actually going to draw them with half arrows. Either the half arrow points upwards, so that's a spin up electron, or the half arrow is going downwards, which is a spin down electrons. All we really care is how many arrows we're drawing. So shell number 1 is still fairly consistent with the Bohr model. 2 electrons max that out, no problem. The first time we start seeing a division is actually on shell number 2. Shell number 2, as we add those electrons, say we go single, 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 and then we start pairing after the 5th one, it makes it look like all 4 of those electrons are all equidistant to the nucleus. All 4 are identical in the same shell there. What we're going to learn here is shell number 2, in fact, is actually subdivided into 2 floors. One energy shell is actually a little bit lower energy, a little bit more stable. Remember, lower energy, the less energy you have, the less can go wrong, more stable. Shell number 2 can also be subdivided into 3 2p rooms. So the 2 marks for us here which energy level we're on. We still belong to shell number 2, but what we're starting to introduce here is because the shells can be subdivided into these orbitals or these sublevels here, we need to identify what kinds of rooms are in. So the analogy that we're going to be working with here is, imagine you were the hotel manager. In front of you here is this energy level diagram. You have the different floors of the hotel. On every floor, you have a certain number of rooms, and your job as a manager is to put the electrons into the different rooms. As we start looking at shell number 2, although we have rooms all on floor number 2, we may have actually 2 different kinds of rooms. One kind of room here may be maybe a 1-bed kind of room. Maybe a P room has a 2-bedroom. They're both on floor number 2, but I have 3 that are of one type, called a P, and then the other type is called a 2S. So those are my subshells here. In fact, this is getting into a little bit of quantum theory here. It gets a little bit more strange as well. Every time we have these sublevels, the S, P, D, and F, these sublevels always contain a fixed number of orbitals. So next point here, subshells always contain a fixed number of orbitals. And going from sort of lowest energy to highest energy here, if you have the S kind of room, the S orbital, S only comes as 1 room per floor. So that's why floor number 1 had 1 of them, floor number 2 had 1 of them. You're not going to have 2 S rooms. So S comes as 1 orbital or 1 room. Whenever we have P's, every time that those kind of rooms show up, they always come in sets of 3. So P comes as 3 rooms. Again, we're going from low energy to high energy. As we get up to our D rooms and our F rooms, I'll start seeing D rooms at energy level 3. We won't get F rooms until energy level 4. We are actually increasing energy going down this way here. So higher energy. We need to go farther up my hotel before those rooms show up. When they actually end up showing up here, the D comes as 5 rooms. So 5 possible rooms for the electrons to enter in, and the F's actually comes as 7 rooms. So it doesn't matter which floor they're on. If they exist, they always come in these fixed numbers here. So we have that sort of listed for us, sort of lowest energy to highest energy here. We're going to have a couple rules here, just like we learned how to add electrons and how the electrons actually enter the nucleus. There's a couple rules that help us do this new electron configuration model. So we're going to start off fairly simple here. First rule that we're going to learn here is the off-ball principle. I'm told off-ball in German means to build up or to construct. This one here is very reminiscent of the Bohr model, that the off-ball principle says electrons, if they have the choice, electrons will enter the closest shell available. Or if you want to frame that different way here, electrons will always enter the lowest energy first. And if you remember the language of ground state is the lowest energy. We're always going to assume things are in the ground state. So they haven't absorbed energy and jumped up to a higher shell. We're going to imagine that they're on the ground floor. So let's just start off here. I'm going to start off with a comparison here of just the Bohr model and then compare it to our new electron configuration model. We'll see some similarities and some differences here. Let's start off fairly simple here just with the hydrogen atom. Hydrogen only has one electron. The Bohr model adequately describes it. So hydrogen's nucleus here, you have an infinite number of shells available. Given a choice, that first electron would just be on n equals 1, just on shell number 1. What we're going to look at now for our electron configuration model is we're going to look at the energy level diagram. We could have said, well, the Bohr model here has an infinite number of shells. Same idea with the electron configuration model here. Well, we actually have many, many floors on this hotel. It doesn't mean that all those floors have to be filled up. It depends on how many guests that you have. In this case here, because you only have one guest, electrons have this sort of fear of heights. They arrive at your hotel. You tell them, well, I have room on floor number 1 available. The electron will take it. Because in that case there, the electron with the negative charge is the closest to the positive charge here. That's going to make it the most stable. So sort of remember our energy level diagram here. It's kind of like plotting a distance, but really this is plotting the potential energy for being so far away. But in this case here, well, an electron arrives at your hotel. On floor number 1, we only have the lowest energy kind of room, the S kind of room. So we're going to call it a 1S. And again, we're just going to change our notation here. Instead of a dot, we're just going to do a half arrow going upwards. Say it's a spin up electron. Now, I don't always want to draw this energy level diagram. As we'll see in this lesson, the more electrons we have, it gets very tedious having to draw this. So what I'm going to do here, this is my new model. We're calling this the Electron Configuration model. The configuration of electrons is basically a roster of where all the electrons are in your hotel. In this case here, I only have one electron. We're sort of building up from the ground level first. In my floor number 1, in my S kind of room, we happen to have one person inside. The electron configuration for the hydrogen atom is 1s1. So let me just map this out for you here. The big number in front, this one here is the main energy level. So it's the main shell. We're on floor number 1. Fine. The S tells you what kind of orbital we're in. This is going to be the orbital. It's either SP, D, or F. Those are the orbitals that we have. Strange letters, but they're placeholders for now. And then this one here that looks like a power, it actually just tells you the number of electrons. As you can imagine, as you get more electrons here, this roster is going to get longer. It's going to start looking like gibberish. But all you're doing here is you're trying to make a listing of where all those electrons ended up. All right, so that was our first principle here. We will keep with that principle. As we start getting to things with more electrons, we now go to enter rule number 2. Rule number 2 here says, Pauli's exclusion principle, there's a limit to how many electrons can fit on either shell. If you remember back on the Bohr model, so far we said, well, the first shell being close to the nucleus, it maxes out at 2. Or the second shell here is a little bit further. This one here maxes out at 8. This Pauli exclusion principle is sort of reminiscent of that idea as well. So remember, whenever we develop a new model, we want to try our best to keep it consistent with older models. If it's not consistent, either it's an exception or we need to come up with an even bigger model to try to pull the models together. So Pauli exclusion principle basically sets rules for each of these rooms. You may have S rooms, P rooms, Ds, and F rooms, but basically says each one of these rooms here, called an orbital, each orbital can hold a maximum, just like there was a limit on the Bohr model, a maximum of 2 electrons, so very reminiscent of our very first shell. And the idea here is they have to go in with opposite spin. Again, I sort of alluded to it. Electrons have this property here called spin. The analogy that I have is, let's say this is the planet. Our planet is always rotating on an axis here. Let's say we're rotating here clockwise. If an electron were doing that sort of rotation, I might refer to it as a spin up electron, and I'm going to use the half arrow up to show you that spin up. If the electron actually along that same axis is actually twisting in the opposite orientation, counterclockwise here, we'll call it spin down. As long as it is outside the atom, it can change spin, no problem. It can be an up spin, later it can be down spin, whatever. But what we're going to find is by the time you actually enter into the rooms, if one of them has gone an up spin, the other electron has to make sure it's a down spin before it's actually able to enter. So just by convention, we always put in the up spin going first. It really could have been the down spin going first. The limitation was just that second electron who would pair up with it has to be the opposite spin. Now this limit here seems really restrictive. If every room can only hold 2, where do I get back the Bohr model here with 8 electrons? So keep that in the back of your mind here. We're going to step through a few other elements to see if we can explain that. Let's take a look at lithium. Really all you need the periodic table for here is just identifying how many electrons that we're going to end up drawing. Lithium here has 3 electrons. So the Bohr model can accurately describe it here. There's our nucleus. First 2 go on shell number 1. That's closest to the nucleus here. The third electron is out of luck. It's going to then take the next shell out. Fine. We're going to look at the energy level diagram here. The energy level diagram here, again, is specific to each element. The energy spacing, the staircase might be different, but at least per every element will have a 1s kind of room. Every element will have a 2s kind of room or a 2p kind of room. It's just that the energy spacings might be different between one element and another element. So let's use our rule so far. We have 3 people arrive at your hotel. They all have a fear of heights. It's your job to put them all into the hotel. First guy, fine. No one's in yet. Let's just go in. Again, convention's sake, we'll just go in the up spin. Second guy has that decision. He has a choice. He could pair up with the first guy. Well, he really doesn't like that first electron. There's some repulsion, but he likes the fact that being on the first shell here would be close to the nucleus. That's the compromise here. The second guy, when he goes in, he's going to actually go in with a down spin. He just wants to be a different spin from the person earlier. That's Pauli's exclusion. It says, okay, that room is completely maxed out. It can't handle any more. First shell holds 2. At least that's consistent. Where does my third electron then go? The third electron also wants to be close to the nucleus. However, because the first shell is full, the second shell takes the elevator up. On floor number 2, there's S kind of rooms and there's P kind of rooms here. The S kind of rooms are still lower energy. We just sort of build up lowest energy to highest energy here. That electron goes into the 2S room here, and there we go. That's what the energy level diagram would look like, and the electron configuration will basically be a roster. Well, where do all 3 electrons go? First 2 electrons went into 1s, so as writing the electron configuration, I'm going to say 1s happens to have 2 electrons inside, and then we have a 2s room, and there's actually 1 electron, that one there. 1s2, 2s1 is actually the configuration for lithium. It's a roster, it's a listing of where all those electrons ended up. Alright, so let's just keep making it a little bit harder here. Let's jump over to, let's say, oxygen. Oxygen has 8 electrons. Again, I'm going to just sketch out the Bohr model here. We're just going to be able to compare what the Bohr model that we're familiar with here so far and compare what it would look like on the electron configuration model. So again, oxygen here has a couple more protons than lithium does, so the staircase is all different. At least the ordering of which shell is going to come up next, it's always going to be the same. So maybe shell number 1, shell number 2. Shell 1 is really low energy. We only have the S kind of room always. Shell 2, we started saying, can be broken up into subshells. We can have a 2S kind of floor. We can have a 2P floor. Whenever the P's show up, it always shows up in sets of 3. And this time what we have 8 electrons show up. And again, we as a hotel managers, we just need to put the electrons on to the different rooms. So let's try it out here. First 2, for sure. Let's squeeze them into the 1S here. 1 goes in upspin, 1 goes in downspin. That maxes out that room. The next orbit out from there here, the next 2 electrons here, one of them is going to go in 2s, the other guy is going to pair up and then go in the other 2s here. They don't necessarily like each other, but again, energetically here, the lower energy, we're following the alpha principle. That actually doesn't coincide with the Bohr model. Remember, for the Bohr model, especially when I add those electrons in the second shell, I would actually add it single. I actually add them individually, so they go in by themselves first. In this case here, they've actually gone in together. So we're starting to see, in addition to this sub-level discussion here, there are parts in the electron configuration that are not quite consistent just yet. It's more interesting what happens to these last electrons. So to explain these ones here, I need to introduce the one last rule we're going to do. So far we've had the off-ball principle. Electrons enter the lowest energy first. They always build up bottom up on that staircase. Pauli said every single room has a limit of only 2 electrons. They always max out at 2 with opposite spins. And this third rule here, We're going to call this Hund's rule. And Hund's rule, although it's worded quite strangely, electrons enter singly. They enter one by one when they're going to introduce another vocabulary here, degenerate. That word degenerate just means equal energy. Orbitals are available. So we're going to see this as an example in oxygen here. So far, we've said the 1s is more desirable because it's closer to the nucleus, the N2s. Now that the p rooms actually come in 3 rooms here, you'll notice all 3 p rooms are actually at the same energy reading. These 3 p rooms are said to be degenerate. Again, that means they're equal energy. It means all 3 of these p rooms here are equally, they look the same. They're all sort of equidistant from the nucleus. There is an advantage for one room over the other room. So far I have 4 more electrons to put in. 3 of the p rooms here, again, just by convention, we put in the upspin first, and I usually just go left to right. So first guy goes in, he's going to go in upspin. The 6th electron here now has a choice. Out of these 3 rooms, one of them already has 1 electron. It's not quite maxed out yet. So if you were that 6th electron here, you could, hypothetically, you could squeeze in next to this person, or you could take your own room. In this case here, Hund's rule guarantees for you electrons have this funny principle. They're going to go in singly. They're going to go in by themselves unless there's no other choice. And the way we're going to understand this here is we're going to picture this is exactly what we do when we get on a bus. So let's just say our bus mentality. Let's say school's over and you go line up at the bus stop. Really short bus pulls up this time. So this really short bus here happens to only have 3 seats on the bus. You know those bus seats here are always sort of built in pairs there. You're the first person on the bus. You're like, sweet, empty bus. I can take whatever seat I want. I'm going to go in this first seat. Second person gets on. He notices, yeah, there is a seat here. If you don't know the first person here, it would look really strange if you're like, yeah, I'm going to sit beside this person, right? Why not, right? In fact, what you'll probably do is you'll say, okay, yeah, I know there is a seat available for me, but I'd rather, have more leg room and I can stretch out here. I'm going to rather take my own seat because I really don't want to sit next to someone if I don't have to. Third person gets on, exactly the same story. Oh no, 2 of the 3 seats are filled up. Oh, phew, there's still 1 more seat available. Third person goes on, gets on his own seat. Fine. So far we filled in single, single, single. Then the 4th person gets on the bus. He would rather not stand. Maybe he has a really long bus ride. It will look a little bit less awkward if the 4th person, even if they don't know them, they're maybe a stranger here, but they're going to sit next to this person. That won't look overly odd. So electrons do the same principle. The reason why electrons do this is, remember, electrons have a negative charge. Given a choice, do they want to squeeze in next to someone that's also negative? Not really likely. It's like you getting on a bus here and your worst enemy is on the bus here. You wouldn't want to sit with them unless there was no other choice. So electrons are going here single, single, single. That's reminiscent of with the Bohr model when we went single, 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 single. We saw it was a little bit not matched with the first 2 electrons. But by the time we have to pair up here, fine, I'm going to match up with one of them, match up with another one. I have that next electron, and there we go. Let's double check that we're following the Pauli exclusion principle. Pauli says every room can only handle 2. Great, we're following that rule. It's just because I have 3 of these p rooms. That's why in total I actually have 4 of these p electrons. So we're going to write out the configuration here. I don't want to have to draw this energy level diagram again. So what's going to happen here is we're actually going to do electron configuration 1s2. There's 2 electrons on floor 1 s kind of room. The next 2 electrons are on 2s, so we're going to go 2s2, and the last 4 electrons are on 2p. And just remember, p comes as 3 different rooms, and that's why we can actually fit in 4. They go in singly whenever there's degenerate ones available. So I'm going to just look at just a generic hotel diagram here. So far we're starting to practice building in some of those lower shells here. A couple keynotes I want to show you on this energy level diagram. Remember, every single element will have its own hotel diagram. Every element has a different number of protons. The staircases, the energy spaces may be different. However, at least the ordering of the rooms here is always going to be the same. Shell number 1, like we mentioned here, low energy, it's fairly boring. You only have the S kind of room, the lowest energy room. Shell number 2 divides into 2 kinds of rooms. We can have the S rooms, we can have the P rooms. S shows up as 1, P always shows up as 3. Each one of those rooms is called an orbital. Each one of them can handle 3 electrons. Now we get something strange happening at n equals 3 and n equals 4. Let's take n equals 3. So this would be the third shell out from the nucleus. Because we're now higher energy, we now start seeing our d orbital shells. So our energy level 3 here splits into 3s, splits into 3p, as well as splits into 3d. Whenever the d's first show up here, well, d's always come in sets of 5. That's why we actually have 5 energy levels there. So when you take the elevator up to floor number 3, you realize that there's 3 kinds of rooms. There's a total of 9 rooms that you can end up sitting in. Each room can max out at 2. Notice what's end up happening here is, if I compare shell number 3 to shell number 4, shell number 4 is even further from the nucleus, it's even higher energy. Shell 4 has also separated into an S kind, a P kind, a D, and an F. You'll notice on this energy level diagram there's no x-axis. They're just trying to keep the S's and the P's in the same column so you can see it easier. What you'll notice strangely is for every single element, shell 3 has divided into 3 levels. Shell 4 has divided into 4 levels, but by the time they've divided, I noticed that my shell 4, you look at its energy reading, the energy level here is actually lower than where your 3Ds had actually split into. So technically here the D's belong to shell number 3. But if I just offballed, if I just build up from lowest energy first, as I fill in electrons, as I fill in 3s, 3p, I'm ready to fill in the 3d. But wait, 4s is actually lower energy. So long story short here, we're just going to fill in the 4s's before we come back and we fill in the d's. We just go sort of lowest energy, highest energy. While I have the diagram on the board for you here, we're going to find as we get higher and higher up from there, shell 5, shell 6, and whatnot, this sort of, shell 4 actually ended up lower, or shell 5, or that sort of mix-up gets to be a little bit more intense, so we're going to get lots of exceptions by the time you get to the bottom of the periodic table. Your question might be, alright, so if I gave you this hotel diagram, we would offball, we just build up, we go maybe first 2 electron go in 1s, then here, right? We can probably fill it in, we do Hund's rule. We better be given this on test, right? Unfortunately, no. Unfortunately, we're not given this energy level diagram. However, there's a really easy and a nice memory aid. Based on how we actually organize the periodic table, I can actually predict which is the next shell to actually come up. So I'm going to actually give you 2 ways of memorizing this, okay? Which sort of orbital comes up next, and we'll just end off just practicing a few more electron diagrams. So one way here is to sketch out a diagram. I don't particularly like this one here because this one here takes a little more work, but so be it. So I have my S's, 2p, 3p, 3d, 4p, 4d, 4f, 5p, 5d, 5f, 6p, 6d, and 7p. So this way of memorizing here is sort of like a chart diagram. You would have to draw out the chart. That's the first thing. And then what you can do here is you can actually predict. If I start from sort of the top right corner, first shell here is going to be 1s. Next shell here is going to be 2s. Then the next shell is going to be 2p and then 3s. Remember earlier we said 3p and then it should be 4s next. As I follow this direction here, it's 4p, then 4s. Then we go 3d, 4p, 5s. So at least this way of reading it here will actually give you which orbital shell comes up next. Again, I don't particularly like this one here. I actually prefer the next one. It's actually on the back side of this resources sheet here. The second way here is just using our periodic table. And just let me sketch a periodic table and then we'll look at the summary diagram. Our periodic table here roughly looks like this. What we're going to do is for this memory aid, we're going to divide our periodic table into the 4 corresponding sections, the S, P, the D, and the F. Just for the purpose of this memory aid here, this first one here would have been hydrogen, we would have helium here. Imagine that the helium is sitting right beside the hydrogen, just for the purpose of the memory aid. We're going to divide our periodic table up into the first 2 columns. These ones here are going to be S block, these are going to be S electrons. The last 6 columns, sort of going from boron down to neon here, the latter 6 columns here are called P block. Those are going to go in P rooms. We're going to have the middle rooms that are D block. Those are your transition metals, so D block. And then those inner transition metals here, those 2 rows are actually pulled completely out of the periodic table. There's actually 14 electrons inside there. This one here actually is F block. The electrons going into those ones are actually F electrons. So this is sort of, we've separated it good. It corresponds with the SPDF. And now we just need to see which energy floor we're going to be on. S's and P's are really easy. We're going to start from row number 1. This is n equals 1. Let's say I started with hydrogen. Where is hydrogen's electron going to go? Hydrogen is sitting in row number 1. It is S block, and it is the first electron in. Hydrogen would have the configuration 1s1. How about helium? Helium here is also row number 1. It's also an S block, but helium is actually the second element in. So helium would actually have hydrogen's 1s1 and add the second electron, so in total 1s2. We did lithium earlier, so lithium is sitting down here. Lithium, it's actually now on row number 2. It's sitting in S block, and it's the first electron in. Lithium should end with 2s1. However, lithium here has 3 total electrons. We still have to include all the electrons on the inside. And we know that helium had sort of finished off that shell there. So lithium will have the 1s2 and also a 2s1 to end off. So based on where the element is on the periodic table, we can actually make a prediction of how many electrons do I build up to until I finish. So for example, if we're looking at oxygen here, it's boron, nitrogen, oxygen, sorry I missed carbon here. Boron, carbon, nitrogen, oxygen, you have your periodic table. So nitrogen, oxygen like that. If I made a prediction, I just want to double check, did I get oxygen's configuration right? Oxygen here is row number 2. After you fill in 2s1, 2s2, we're still in row number 2 for boron, but now we've entered into P block. We start getting into that kind of room. This is the first element in, second element, third element. Oxygen is the fourth element in. This one here should all have all the electrons until row 2, P block, the fourth electron. And again, as we build up to that here, we just show all the inner shells being full. The 1s2, first shell can only hold 2, then the next shell up from there, 2s2. So the S's and P's are fine. We had separated it. S's and P's follow the row number. Just be careful when you actually do the D block here. We'll touch on this a little bit more in tomorrow's lesson as well. In this case here, this would have been row number 4 with potassium and calcium. So these are 4s electrons. When the transition metals come in with their D blocks, when they first arrive, remember the splitting here is the 4s was actually before 3D. Technically, we're actually on row number 4, but just for the purpose of the memory aid here, just remember the D blocks are 1 row shorter. So if this is row number 4, we're only 3D. If we're 5s, this is only 4D. And again, we can count 1, 2, there's actually 10 elements going through, and that'll actually tell you how many D electrons there are. So shell D is actually 1 row shorter. If it doesn't, doesn't fuse as yet, we can actually go to the last row here. We would actually have 6s. It would be 5D, which is 1 row shorter. When the F's first come in, just memorize for yourself here, the F's actually come in 4F first, and then 5F. I have a nice summary chart for you on the bottom here. We're just going to be given the regular periodic table, but as you're learning it, this is how we're doing it. Notice the S's and P's follow really nicely the row number. The row number actually gives you what shell you're on. Notice when the D's first come in here, is actually starting in row number 3. The 6s, which would have been 5D, the 4F row here that would have come up here, it's not 6 with a row number, it's not 1 shorter, it's actually 2 shorter. So just remember the actinium row here is actually 4F and the 5F for the bottom row. So just let me leave you with that. Let's just practice through maybe 2 more. How this question here will be worded is just simply here, write the full electron configuration. Full meaning, give me a full, complete roster of where all those electrons ended up. Let's try to do it here for scandium, our first transition metal here, and let's do one more practice. Let's go down to maybe krypton. Right? So you can still use your electron configuration diagram, right? Just for the time being. You can go shell 1, shell 2, right? You can start doing this subdivision yourself. All we're really doing here is we're just putting them into the many different kinds of rooms. Just remember, by the time we start getting into the 4s, we start seeing it for scandium here. Scandium actually has enough electrons. By the time shell 4 is actually separated off, 4s is actually lower energy than 3D. So if we end up off-balling, I build in those 4s electrons first. So I'll do scandium for you, and I'll leave krypton for you to try. First thing you're going to look at is the number of electrons on the periodic table. Scandium actually has 21 electrons. First 2 go in here. Next 2 go in here. Then we're going to do Hund's rule. 5, 6, 7. Pair, pair, pair. That's 10 electrons. Next 2 go in here. 12. We do our 100 again, single, 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 pair, pair, pair. That's 18. Here's weird, but we're actually going to enter shell number 4 before we enter shell number 3, finish with shell number 3. So we're going to go 1, 2, and then 1 in that case there. We just off-ball, we just build up lowest energy first, regardless of it's just whichever energy level comes in first. And our full configuration is just a full roster. So in 1S, we have 2, 1S2. In 2S, we have 2. In 2P, we have 6. In 3S, we have 2. It's going to look like gibberish because we're getting more electrons, but all it is here is a listing of where all the electrons ended up. If I added up all these superscripts here, it should add up to the total number of electrons, because for a full configuration, I told you exactly where everything was. Let's just make one last comment here with the Bohr model. First shell holds how many? First shell maxes out at 2. Great. Those 2 are actually S electrons. Second shell maxes out at 8. In this newer model here, we're saying shell number 2 actually subdivides into a 2S kind of room, 2P kind of room. Every room maxes out at 2, but given the 4 total rooms that I have, I'm going to max out at 8. Great, that works. Third shell here, we were sort of a toss-up here. We can say 8 or 18. We would say 8 if we're considering just the S and P. Tomorrow we'll call those valence electrons. So max of 8 is actually correct. And yet if you look at energy level 3, wait a second. There actually were some D electrons on energy level 3 as well. In total, there's 5 D rooms, so 2 people per room. So this can actually max out at 10 electrons. So if you count those 10 D electrons, that would actually be 18 electrons, and I think this is now consistent. So there we go. Use your energy level diagram for the time being. See if you can match it up with the memory aid, and try to get this ordering without actually staring at the diagram every time. If you have any problems, just let me know. We'll pick it up from there tomorrow. Thanks, guys.